Now let's wrap up our discussion by considering if we added more NaOH beyond the equivalence point. So this would be 26 milliliter of NaOH. If I do this, now my NaOH is just slightly more than my acetic acid. So at equilibrium, what I have is 0.1 millimoles of OH minus and 2.5 millimoles of acid. So what solutions do I have? I have a combination of solution. I have a strong base and I have a weak base. Whenever we have a mixture of things, they're the same, right? Strong acid, weak acid, or strong base and weak base, is the strong species that are going to be important in determining the pH, right? So the weak base species is going to be there, but it's not really going to matter that much. We've shown that calculation again and again in the acid-base equilibrium chapter. And so right now, when I look at these two species, this is how much strong base I have, this is how much weak base I have. You can see that there's more weak base here, but if you go ahead and calculate how much OH minus actually is produced by that weak base, it's much smaller than this number right here. So in the end, all I need to do is just take the negative log of this to give me my pOH, and then I just subtract 14 minus that number, and I would get a pH of 11.29. And so that's the number that would go here in my table as my pH, 11.29. Now, in fact, that's what you're going to do for the rest of this, is that once you get into that range, all you have in your solution is just a strong base. It's a combination of strong and weak bases, but then it's the strong base that determines the pH in the solution. And so what I've done here is summarize all of those numbers in the table with all the parts that are blank before now filled in. You should calculate all of these and make sure that you get exactly the same numbers that I got, keeping in mind that there's different regions here. This is weak acid, and then we're going all the way here, it's buffer, and then this is the equivalence point where we have a weak base present, and then once we're here, we have a strong base present, okay? Now it's time to draw the titration curve. So the same way as we did the strong titration, we want to have pH on the y-axis and volume of our titrant, which is NaOH, on the x-axis. And generally speaking, the main difference is with a weak strong titration, like in this case weak acid, we start at a higher pH, so 2.87 is higher than our starting strong titration, and then we immediately go into this buffer region where the shape of the curve is relatively flat, and then afterwards we move up to the equivalence point region, which is basic, and then the last part is going to be pretty similar to that strong titration, because at that point all we have is strong base right there. So there's 4 regions in a weak strong titration, and I'm going to highlight it here in the actual plot that I made of the titration that we just did. This one just has a lot more numbers compared to the one that we did here. That's because I did the calculation in Excel. I was able to calculate with a lot more values, and so the plots is a lot more defined here versus the one that we did. But what you can see is that at the beginning, it starts at a higher value, and then afterwards it gets into this fairly flat part, and then it goes steep when you reach the equivalence point. Then afterwards it's pretty much similar to the strong titration. So what are the different regions that we have? That corresponds to the regions that I mark here on the table, which is the weak acid, the buffer, the weak base, and the strong base. So at the beginning we have a weak acid, and then afterwards this entire region here is where the solution that we have is just a buffer. And then here we have the equivalence point, which happens to be a weak base for this particular titration. It's not always the case, right? But for this titration, it is a weak base. And then lastly, when you get to this part, all we have is strong base that defines the pH, okay? This is a comparison of the actual plot of a strong acid and weak acid titration using the same starting concentration for both acids. As you might imagine, the strong acid starts at a lower pH, so even though you have the same concentration, the weak acid is not going to be as acidic as a strong acid. Now, the part that they start to look the same is starting from this part right here all the way to the end, which is basically once you hit the equivalence point of the weak strong titration, part starts to join in as well, and then at the end, that's just the strong base region. So they both look identical, because once you get to this point, it's really just strong base that's driving the pH calculation. All right, this is the opposite type of titration. In this case, we have either a strong base, which is this one right here, strong base titrated with strong acid, so that's the strong titration, or we can have a weak base titrated with a strong acid. And so again, it's kind of a mirror image of this plot right here, the plot shown for the strong and weak acid titration. With this one, the strong base is going to start at a higher pH, even at the same concentration. The weak base is going to start at a lower pH. And then again, what happens here is that it goes into the buffer region, whereas in the strong titration, there's no buffer, right? Just the strong base pretty much in excess throughout until you hit the equivalence point. So the equivalence point for the strong titration is still 7. So you can see that that's the equivalence point for strong. That never changes. So just always keep that in mind. Whenever you do a strong titration, the equivalence point is always 7. That's when the number of moles of the strong acid and number of moles of strong base are exactly stoichiometrically equal. So all you have in your flask is water. This black dot right here represents the equivalence point for the weak strong titration. So in that case, you can see that the pH is actually less than 7. It's more like around 5.2 or something like that. So that's an acidic pH, which again makes sense because what happened with a weak base that's been titrated with a strong acid? So just think about the reaction here. The reaction is going to be A minus plus H plus, which comes from the strong acid, forming HA. Right? If you think about this as being equal, so let's say this is 1 and this is 1 and this is 0 and then minus 1 plus 1. What do you have at the end? All you have is a weak acid solution at the end. So a weak acid is going to have a pH that's less than 7, and that's the reason why we see that spot appearing. So again, keep in mind that in a weak strong titration, your equivalence pH is not 7. Okay, the last part that I want to bring up is the concept of polyprotic titration. This is not as critical as understanding those monoprotic acid and base titration that we just did, but you do need to know something about this because you're going to be dealing with some polyprotic acid. Polyprotic acid, the way you can think about it is sort of like adding up all of the different monoprotic acids. So if I have a triprotic acid, for example, it's kind of like having 3 of these weak acid, strong base titration kind of stacked up on top of each other. So here's an example. This is a triprotic acid, phosphoric acid, and it's being titrated with sodium hydroxide. So you can see there's 3 different half equivalence points. The first one, this is the second one, and this is the third one. And there's also 3 equivalence points. This is the first one, this is the second one, and that's the third one. Because there's 3 protons that the hydroxide has to neutralize. And that's why there's 3 of both of the points right there. The key here is to know how to calculate the different pHs. The steps are pretty much the same. So at the half point, whether it's the first, second, or third, if you have the third one, the pH is always just going to be equal to pKa. So if you have 3 different dissociable protons, then at the first half point, pH is going to equal the pKa number 1. Second half point is going to equal pKa number 2. And then for this one, if you have the third half point, the pH is going to equal to pKa 3. Okay. The complication comes about in calculating the pH at the equivalence point. So it turns out it's not as easy as what we had done in the prior step. The reason is because when you're at equivalence point, so for example, if you think about the equivalence point of diprotic acid, okay, you're adding OH minus and you're forming HA minus, that's the first conjugate base, right, plus H2O. And so at equivalence point, just let's say we have 1, 1, 0 here, we have minus 1, plus 1. So this looks something like that. We now have HA minus, okay? But the reason HA minus is unique is because it's an amphiprotic species. It could go to become acid, it could also go and become base. So there's 2 reactions, and in one reaction, it's gonna rely on its Ka1, in another reaction, it's gonna rely on its Ka2. So as a result, when we calculate the pH at equivalence point, when we have multiple dissociation steps, we're going to take an average of the pKa's to get our pH. So for the first equivalence point, because you have HA, which is the product of the first dissociation, but it's also going to go on to dissociate into A2 minus and H2O, right? That's the second dissociation. So as a result, we're going to have to combine pKa1 and pKa2 to calculate our pH at first equivalence point. So that's actually shown here in this picture. For the first equivalence point, we use pKa1, pKa2 divided by 2. When you're at the second equivalence point, which is this one right here, now you have the second species, and it's between step 2 and step 3, so you're going to take pKa2 plus pKa3 divided by 2 to get your pH. What about the third equivalence point? Well, at that point, you're done with your titration. All you have at that point should just be your final product, which is a phosphate ion in this particular titration, and nothing else. So then all you need to do is the phosphate ion to calculate your pH, using KB and an ice table to help you find the correct pH. That would be the same step as we did earlier when we were calculating the pH of the equivalence point with the monoprotic acid. So that part of it is the same, but it's really the part in between that's going to be a little different, where we have to take an average of two pKa values, okay?